that I was disenchanted with statistics. When I was a student, I actually didn't like the topic at all. And the reason was that I thought it was intellectually uninspiring. And what I hope to demonstrate to you today is that it actually also doesn't really address the questions of interest. And I'll argue that Bayesian statistics does. So my goal today is very modest. I'm not going to argue that Bayes is superior to classical inference and we should abolish classical inference, even though I do feel that is the case. I will just argue that it would be a mistake to ignore Bayesian inference. And it would be wise to use Denny's term to present both the classical conclusions, the frequentist conclusions, and the Bayesian conclusions side by side. So first off, it should be clear that Bayes is not a magic potion that protects you against ignorance. It doesn't redeem you of your statistical sins, and it doesn't address all questions that you could possibly ask. Bayesian statistics can be abused and has been abused and will be abused just as any other statistical method. However, if you want to learn efficiently, if you want to adjust plausibility assessments for hypotheses or parameters according to their predictive performance, then you have to resort to Bayesian statistics. So the issue of subjectivity and objectivity always comes up when you discuss Bayesian statistics. And I want to clarify a few things there. So first of all, is Bayesian statistics subjective? So you could say yes, in the sense that we take our existing knowledge and we apply it to ask a meaningful question. So in that sense, it is subjective. But this is not the same as arbitrary. Right? When people accuse Bayesian statistics of being subjective, they don't mean it's inspired by knowledge. They mean to say it's arbitrary, but it's not arbitrary. Every Bayesian with the same background knowledge draws an identical conclusion. That is, I may add, a fact. So what else is subjective in science? Developing a theory. I always like to point out that Denny himself has developed several interesting theories, and his work is in that area is completely subjective. So proposing interesting predictions is subjective, and designing an informative experiment is completely subjective as well. So basically, from bottom to top, science is a subjective enterprise, but that's very clearly different from an arbitrary exercise. So I could continue and talk about the philosophical pros and cons for a very long time, but let's just discuss a concrete example and see what we can do. So what we're going to look at is a specific data set. We're going to look at movies by that feature Adam Sandler, and we're going to look at whether there is a correlation between movie quality as indicated by freshness ratings on the Rotten Tomato movie website, and box office success in millions of US dollars. So here you already see the scatter plot, and from the scatter plot you can detect that there's not much of a relation here. Right? So that's a little surprising, because maybe you'd think that good movies attract larger audiences, but that appears not to be the case for Adam Sandler. But what is going on here? We certainly have a statistically non-significant result, but do the data provide evidence for the null hypothesis, or is there just a total lack of evidence? In order to find out, we will now do a Bayesian analysis in JASP, and I'll do a classical analysis as well. So I was told that you have not encountered JASP in this course. Did Johnny van Doorn show you JASP in the first year, perhaps?
Yes. Yes, he did. Yeah.
He did. Okay. So then you are familiar with it already. So we've improved it since. There's a new version just out, and let me show you how it works. So you now see JASP, I hope. Yes. Yeah. Okay. Good. So I've already opened JASP. We're going to open a data set, one that's in the data library. Under regression, you will find the Adam Sandler data set. And if you click here on the JASP file, you see an annotated description of the results, but we're going to analyze the data from scratch. So I'm just going to open the data file. So here you see the year in which the movie was made or came out. So it starts at 2000, and I collected this data set in 2015. Then we have the freshness ratings on Rotten Tomatoes, box office success, and the movie title. So for instance, if we look at row 12, in 2005, the movie Deuce Bigalow, European Gigolo came out for a freshness rating of 9% and box office success of about 22 million. And I Now Pronounce You, Chuck and Larry in row 15, 14% fresh, almost 120 million. So let's do a test for a correlation. So we go to regression. Okay, first I'll do the classical correlation, the frequentist correlation. I drag in freshness ratings and box office success. And here well, okay, fine, I'll give you a confidence interval as well. Here you see the Pearson's R, the sample correlation coefficient. It's slightly negative, minus 0.03, right? Tiny negative value. The p-value is not statistically significant at all, and the 95% confidence interval is includes 0, obviously, because the result is not significant, but it ranges from minus 0.38 to about 0.33. What can we now say about the support that the data provide in favor of the null hypothesis? Well, in short, nothing whatsoever. Maybe the conclusion should be that we haven't learned very much and you should collect more data. In this case, this probably means that you request, you send a letter to Adam Sandler asking that he work harder and produce more movies, but it's a little difficult. And even if he were to produce more movies, now you have a problem because you've already analyzed this data set. And if he now makes 3 additional movies, you cannot analyze the new data set completely afresh. You've spent all your alpha on the first data set. This was your test. You cannot do a new test. Right? That would be doing multiple tests without a correction. So this is problematic. So I'm just going to remove this analysis, and let's just do a Bayesian analysis and see what more we can actually learn from doing the Bayesian analysis. Again, I drag in freshness ratings, box office success. And let's just immediately turn to the good stuff. So I'll select, so this functionality is meant for large correlation tables. If I want to look at 2 specific variables, I go here to plot individual pairs. I immediately get the scatter plot, but I'm just going to remove the scatter plot. We already saw that. And I'm going to look at the prior and posterior distribution here. Actually, let me introduce it step by step. So here, the dotted line is the default prior distribution for the correlation between movie quality and movie success, right? So this means that a priori, every value of that correlation you deem equally likely. You can change this, and we will do that in a moment. But that's our default assumption under the hypothesis that there is a correlation, right? So this says if there is a correlation, it could be anything. That's our alternative hypothesis. Then we see the data, and the data update our prior distribution to a posterior distribution that is given by this solid line. So what have we learned? We've learned that high values of the correlation and low values of the correlation are not very likely. The values that are likely are the middle values of the correlation, everything near 0. So if we want to be specific about it, we can say that the posterior median is minus 0.03, and we also get a 95% credible interval. And numerically, this is the same as the classical results, but the numbers mean something different, right? Here you can actually say, I am 95% confident that the true value of the correlation coefficient lies between these two numbers. Right? This is absolutely not something you can conclude from a classical confidence interval. This is something that people very often do wrong. But we can also do a test. So if we click testing info, we see that we can evaluate how much the prior density at a correlation of 0 changes due to the data. So before you saw the data, that credibility of that value was here, and after you see the data, it has increased to here. And the degree to which it has increased is exactly 4.4, which means that the data are about 4.4 times more likely to have occurred under the null hypothesis than under the alternative hypothesis. In other words, the null hypothesis has outpredicted the alternative hypothesis by a factor of 4.4. And why is this? Well, the alternative hypothesis makes these strange predictions of very high values of these correlations, and those predictions do not accord well with the data at all. So the Bayesian paradigm includes an automatic penalty for complex models. Models that are overly complex are penalized. And simple model, parsimonious models are rewarded. So we have some evidence here in favor of the null hypothesis. And what we can also do, so this is something you cannot get from a classical framework, right? What we can also do, which you also cannot get from a classical framework, is a sequential analysis. So what we show here is the degree to which the base factors fluctuate as Adam Sandler makes more movies. So as Adam Sandler makes more movies, as n increases, you see that there's more and more support in favor of the null hypothesis. And the nice thing here is that the Bayesian paradigm is not a paradigm where you have to make decisions. You can make decisions if you want to, but you don't have to. Your primary purpose is to quantify evidence, to learn. And because it's a learning paradigm, this means that when Adam Sandler decides to create new movies, you can just add them to the data set and you will see additional dots appear in the graph. So you can learn from new information as it becomes available without any ad hoc correction or any feelings of doubt.
Erik-Jan.
Yeah.
Could you elaborate on which of the one is of the prior or the posterior you are referring to when you're talking about the null hypothesis?
Yeah. So there are, and that is confusing actually. There are several ways in which the word prior is used, right? So the first one that is the term that's most popular is prior distribution. This is the dotted line you see here, right? This means if we believe that there is an effect, if we buy into the alternative hypothesis, right, then the relative plausibility of the different values of rho, of the correlation coefficient, are given by the dotted line. Right? That's one prior. That's on the level of the parameters within a model. But then you also have the prior probabilities for models. So that's overarching. So you have a hypothesis that says the effect is totally absent. And you have a hypothesis that says, no, the effect is present. And you can also have prior plausibilities on those. But what I'm giving you here with the base factor is the extent to which one hypothesis outpredicts the other. So this is the evidence that the data provide. This is the extent to which you should adjust your prior probabilities for the competing models. So JASP doesn't give you actually in this setting of a t-test the prior probabilities of the models. This is something that is up to you It also differs very much from one person to the next. So this is why in Bayesian inference, there's more of an emphasis on the extent to which the data ought to change your beliefs, not so much on what your prior beliefs are with respect to the competing models. Right, so but it is a little confusing because it's used in two ways. Right, you have the plausibility of the effect being present or absent, and then given that it's present, you have beliefs about what the effect size may be or what the correlation may be. But one thing that should be clear, and that's all I wanted to demonstrate here, is that with just a few clicks, you can get a pretty comprehensive analysis, and you can get at key questions that are unanswerable from within the frequentist paradigm. And I could do other things as well, but I don't want to take up too much time. It's very difficult for me to leave JASP now, but I will steel myself and go back to my presentation. Okay. So there are considerable practical benefits from doing a Bayesian analysis. So we can actually learn from prediction errors. In general, hypotheses that predict the data well get an increase in credibility, whereas hypotheses that predict the data poorly suffer a decline. We can quantify evidence in favor of the null hypothesis if that happens to be the case. We can adjust knowledge on the fly as data come in. And I think most importantly, we can obtain answers to meaningful questions. Right? And the fact that the frequentist results, frequentist statistics, are quite often misinterpreted as if it was a Bayesian methodology, that's not a coincidence. To me, that says something that researchers want the Bayesian answers. Right? Well, if you want the Bayesian answers, you have to use the Bayesian methodology. So those are the Bayesian benefits. So currently, the Bayesian paradigm is mainstream. That is mainstream in statistics. In psychology, the curricula lag that development by decades. Basically, we are teaching our psychology students the statistics that was taught in the 1960s. And that's a real shame. So a little bit more aggressively, I think philosophical discussions about chance are misused to hide the fact that teachers are simply too lazy or too scared to introduce Bayes into their curriculum. So that's sad. Now, this is a slide where I wanted to complain about Denny's idea that the frequentist concept of chance is elegant, because I think it's quite ugly. But I think in the interest of time, I will just skip this, and we can we'll probably get to this in the discussion as well. So let's skip that slide and go to the conclusion. The Bayesian framework offers concrete practical advantages, and that is increasingly recognized. So it is simply a missed opportunity that the Bayesian framework is severely undervalued in your statistical training. I should say, this is already, what you are experiencing is already very, very different from what it was a few years ago, right? So now we actually managed to teach Bayes in the first year, right? And this is, I think this is amazing. I think this is a big win for us and for you as well. And there, but unfortunately, there are very few psychology educational programs, curricula that do the same thing. Usually, people are just bombarded with frequentist statistics, and once they're completely brainwashed, the Bayesian a few Bayesian lessons are added as an afterthought, and I think that's a shame. Thank you for your attention.